Hello, this is Rafael Alvarado and welcome to Exploratory Text Analytics. In this video, we're going to look at how to evaluate model performance for a classifier like naive Bayes. Here's a screenshot taken from Drafsky and Martin's text. Basically, the key to all of performance evaluation with classifiers of this kind is something called a contingency table, sometimes called a confusion matrix. And basically, it's just a concise way of comparing predicted labels with actual labels. The actual labels being, sometimes called the gold standard or ground truth. So here you have on the vertical axis an opposition between the system output labels. That's the stuff, the guess, if you will, what your system predicts will be, whether it's positive or negative. And realize that positive and negative here just stand for any two values. Maybe you're just trying to distinguish between A and B, or maybe you're just distinguishing the presence or absence of something. Positive and negative, you often hear that in the medical space about whether somebody has a disease or not. So that's why it's called positive or negative. So testing positive is oftentimes a bad thing. We think of the word positive as like, good connotations, but no, to be positive means yes, you have X. But just be aware that this is true. This applies to this matrix here applies to any sort of two-valued comparison, but also there are variants of this which we're not going to get into, which apply to n values. You can have a confusion matrix with any number of values on the x and y axis here, or on the vertical and horizontal axis. But generally, what we're interested in text analytics are the two values that you see here, recall and precision. The number of accuracy in the lower right is sort of your instinctive way to evaluate models, but it's not always the best. For example, let's just say that you have a value, you're really trying to, it's a needle in the haystack problem, and you're trying to classify, a document about, whether there's, spam, maybe let's think about something a little more serious, like maybe there's some, secret information that you don't want to get, that you don't want your company to leak. And you're sort of monitoring all of the messages of your company's output email all day. But if you are wrong just once, you basically lose. There's some secret information that gets out, that's some important industrial secret, and once it's out, you lose your market advantage and so forth. So imagine building a classifier trying to detect whether that message has been sent out on a given day. Well, the simplest classifier you can send out is a non-model of saying every single text doesn't have that information. So in other words, everything's a zero. If you do that, you're going to get really high accuracy every time, even when the message gets through, even when the bad message gets through, because the ratio, if you look here, of true positives to true negatives is really high compared to true positives and true negatives plus false positives and false negatives. So you will have a false negative every time that message gets through, but it's undetectable since it's such a small number overall. But it's super, super important. That's why you want to not use accuracy in a lot of contexts. Instead, you want to look at something like recall and precision, which look more specifically at how many true positives you got within all the positives that exist in the world, or how many true positives you got within all the things that you predicted to be positive, right? So there, that value, the email that comes through is going to show up as is going to knock you down in one of those categories. So in terms of our example, if we're talking about positive being, the message is a leak, there's only one case where that's going to be true, right? So our number of true positives given our simple model is always going to be zero. So precision and recall are both going to be zero. So it's a horrible score to get. And so that's why sometimes a lot of times you don't want to use accuracy. So here's another look at the confusion matrix in a way that I'm going to show in terms of conditional probabilities. You can think about these measures as conditional probabilities over this space defined by predicted and actual values of positive and negative. So, you know, just this here is just to clarify in people's minds the semantics here. When we say true positive, we mean that the prediction was positive and it turned out to be true. False positive means the prediction was positive and it turned out to be false. So a false positive is actually a negative in real life. Just so you know what those terms mean. This is this is what accuracy is. It's just taking the true positives and true negatives, the things that are actually that you got right over everything. And remember, if your true negatives are very small but important, this is not a good way of doing things. Here is what is called sensitivity or recall. You see the same word used for both of these. This is where you take the true positives and you divide them by the total number of actual positives. And you can see this as a conditional probability. Is what's the probability that you predicted a positive divided by the actual number of positives, right? Precision is the opposite. It's what is the probability that you actually that it was actually positive divided by the total number of predicted positives. You see how those are, you know, you can see how they're visually flipped, but you can see that they're reverses of each other. See, it's predicted equals positive given actual equals positive, and this is actual equals positive given predicted equals positive. So they're flips of each other in that sense.